All right, so the point of this video is to get you introduced to the idea of eigenvalues and eigenvectors. So this is the beginning of chapter 7 in your textbook. So in general, as we've probably already noticed, matrix multiplication is computationally expensive, especially if you have large matrices where you have to do lots of products of entries and adding them all up together and doing that several times over and over again. However, a scalar multiplication requires fewer computations because you have to take just that one scalar and multiply by all of the entries in a matrix. So the idea behind this, or at least a motivating factor behind this, is that if we can replace an instance of a multiplication by a matrix with a multiplication by a scalar, it can save some time. And when I talk about saving time, I'm talking about matrices that are exceptionally huge, not the matrices that we'll typically deal with in class. But you can imagine that there are large-scale problems in linear algebra that involve large matrix multiplication to be done. So if you can replace it with a scalar rather than a large matrix multiplication, you save some time, save some computational expense. All right, so let's start with the definition here. So let's say we start with a square matrix A, and we have a non-zero vector in Rn. Then we call V an eigenvector of A if we can find a scalar, which lambda is the scalar we typically use. If we can find a scalar lambda such that when I take the matrix A and multiply by V, I could have done the same thing as multiplying the scalar times the vector V. And in this case, the lambda is called an eigenvalue of A, and then V would be the eigenvector associated with that particular eigenvalue. All right, that was a lot of words. Let's see if we can do an example. So let's say we have the matrix 3, 2, 7, negative 2, and V is the vector 1, 1. And we're going to say that our lambda is 5. We'll figure out where these numbers came from here in a little bit in this video. But if I take the matrix A and multiply it by the vector V, I can see pretty quickly that I get the answer 5, 5, which I could have accomplished just by taking 5 times 1, 1, or 5 times the V. So what this shows us is that lambda equal to 5 is an eigenvalue of A, and the vector V, 1, 1, is an eigenvector of A corresponding, and then what's cut off on your screen should say corresponding to lambda equal to 5. It corresponds to lambda equal to 5. It's cut off on your screen where the recording is. So anyway, I apologize for that, but this should just say corresponding to lambda equal 5 because it's the eigenvector corresponding to the eigenvalue. All right, so again, the whole point of this is that this matrix multiplication, taking the A times the V, can be replaced by taking the scalar times the V. And then notice you cut down on computations. To do scalar times the V vector, I had to do 2. Here you would have to do 1, 2, and a sum, that's a third. 1, 2, and a sum, that's another third. So you had to do 6 computations here versus 2 here. That's kind of the idea here, cutting down the number of computations that you actually have to do. All right, so here let's look at another example. Same matrix, different vector, and different value. All right, taking our matrix times the vector, we get the vector 8, negative 28, and if you're astute in looking at this vector relative to the V you started with, and I pull out a negative 4, this is negative 4 times the vector that I started with. So again, lambda equals negative 4 is an eigenvalue of A, a constant we can use, and V is equal to the negative 2, 7 is an eigenvector of A corresponding to lambda equals negative 4. All right, so let's talk about how we find these. How did I know that given that particular matrix A, I knew that those were 2 eigenvalues and 2 eigenvectors? One thing I should mention is that anytime that you have an eigenvector associated to an eigenvalue, any scalar multiple of that eigenvector will also be an eigenvector associated to the eigenvalue. Okay? So how do we find these things? Well, remember, we're trying to replace matrix multiplication with scalar multiplication, right? That's the whole idea. I don't know to start with what the lambda is necessarily and what the x is necessarily. So these are basically 2 unknowns that I need to know. I need to know what the x is, and I need to know what the lambda is. All right, so let's talk about how we can solve this. Well, let's just use some algebra principles back in, Algebra 1 in high school. Isolate the x. That's kind of the point, right? So let's move all our x's to one side. So I subtract the lambda x over. All right, this is hard to combine right now because this is a matrix and this is a scalar, and you're used to being able to combine like term ideas here, right? But I can't subtract matrix and scalar. So I need to be a little bit clever. And I'm going to stick in the identity matrix right in there. So I've got a times x minus lambda I times x, still equal to the 0 vector on the right-hand side. The advantage of this is now I can actually factor out the x to be able to get a matrix that's left over. And I get a minus lambda I times that x equals 0. So this is what I'm interested in solving. This looks like a familiar thing that we've solved before. This is a homogeneous system. We know homogeneous systems are always consistent because I can always plug in 0. No matter what, 0 will do the job to solve the system. But remember, we're looking for eigenvectors. And in the definition of eigenvector, we have to have a non-zero vector to start with. So I don't want just the trivial solution. I want non-trivial solutions. How do I get non-trivial solutions? Well, I will get only the trivial solution if I can move this coefficient, if you will, to the other side. Now, back in Algebra 1 class, to move the coefficient to the other side, you would divide by it. In matrix speak, you would multiply by its inverse. So in order to be able to find non-trivial solutions, I want to make sure that my a minus lambda I is not invertible. Otherwise, I can quote-unquote divide by it and just get x equals 0, which I don't want. So I want to make sure that that we can solve this, get non-trivial solutions. So I want to make sure that my a minus lambda I is not invertible. And we have a condition, an actual function condition, and a numeric condition on when a matrix is invertible or not. And that's exactly when the determinant is equal to 0. All right. So this equation that we are going to try to solve here for lambda is called the characteristic equation of A. So this actually has a name. When we said the determinant equal to 0, that's the characteristic equation. Without the equal 0 part, this left-hand side, think about what you're going to have when you do A minus lambda I. I is the matrix with 1s down the diagonal. So this is going to have lambdas down the diagonal, right? And 0s everywhere else. So when I subtract that from A, I'm going to get something minus lambda all the way down the diagonal. Well, when you do the determinant, you're going to end up multiplying those around a whole bunch of times. But in particular, you're not dividing by any lambdas. You're not taking any square roots of lambdas. You're not doing anything weird to the lambdas except multiplying them together. So this is going to turn out to be a polynomial in lambda no matter what. It's always going to be a powers of lambda. Positive integer powers of lambda, no matter what. So this is always a polynomial, and then we actually give it the name of characteristic polynomial of A. All right, so let's look at an example again. Let's go back to our example that we did at the beginning. 3, 2, 7, negative 2. All right, so here is A minus lambda I. I said that lambda I is when you take lambda down the diagonal, and then we're going to subtract it off of A. Remember, everywhere else is 0, so if it's not on the diagonal, it stays the same. Subtracting lambda off the diagonal, we get the 3 minus lambda up in the upper left-hand corner, and negative 2 minus lambda in the lower right corner. Taking its determinant, this is 3 minus lambda, minus 2 times, or negative 2 times, negative 2 minus lambda, so 3 minus lambda times negative 2 minus lambda minus a 14. So when we simplify that, we get lambda squared minus lambda minus 20. That's a polynomial. That's the characteristic polynomial of A in this case. We solve the characteristic equation, set the characteristic polynomial equal to 0. That gives us the characteristic equation. We solve that to find the lambda. We're trying to find out when this has non-trivial solutions. That happens when we put in negative 4 for lambda or lambda 5 for lambda. We can factor that. All right, so the eigenvalues are the values that give us non-trivial solutions to this homogeneous system. The eigenvectors are the ones that are associated with associated with lambda are the non-trivial solutions. So we know how to find these. If we plug in a number for lambda, we know how to find x. we're going to just plug it in for x into that matrix, and we'll row reduce and solve like we always do. So let's do this example. We found one of the eigenvalues was -4. Plug it in, we get the matrix 7, 2, 0, 7, 2, 0. That one's a pretty easy one to row reduce. You get 1, 2, 7, 0 here in a row of zeros. You should always, always, always get a row of zeros when you row reduce after plugging in an eigenvalue. If you don't, you've made a mistake somewhere, okay? These always, 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 always have to have infinitely many solutions. And you're always, always, always dealing with square matrices. So when you row reduce, you always, always, always have to get a row of zeros, no matter what, okay? If you end up with the identity matrix here, you have done something wrong, okay? Go back and figure out what you did wrong. All right, so here's our solution to the homogeneous system. We see we have non-trivial solutions because we have a free variable, and we know exactly what those are. We move the 2 7s over to the other side. You get -2 7 for x1, and then x2 could be anything. So we get any constant, any t, any scalar t, times -2 7 and 1. Since t can be any scalar that I want, I might as well just do a scalar multiple of this and call it the vector that's generating everything. So I can multiply both components by 7 and get this t times -2 7. And notice the -2 7 was the eigenvector I started with in the example that we started this video with. Okay. Again, this whole t being out here tells me that not only is this an eigenvector, every single scalar multiple of this vector is also an eigenvector. Okay. No matter what I multiply this by, if I do the matrix times that vector, it's the same as multiplying the scalar times that vector. Okay. We get a whole space of eigenvectors. We actually refer to that as the eigenspace of the matrix associated with a particular eigenvalue. All right, let's do the other eigenvalue. Lambda equals 5. Subtracting 5 off the diagonal, we're left with the matrix -2, 2, 0, and 7, -7, 0. Again, row reducing this is no sweat. We get 1, -1, 0 in that top row. So we see here that the solutions are any constant times 1, 1. So again, the 1, 1 was one of the eigenvectors we saw when we started this example. All right, why do we care? Well, I mentioned this a little bit before. Well, let's say I want to do this matrix product, which again, not hard. We could do this. This is a small matrix. So imagine that I'm multiplying a matrix with hundreds of entries in it, not just 4, okay? All right. Well, let's suppose that I knew that this -225 is this linear combination of the -2, 7 eigenvector and the 1, 1 eigenvector. Well, what can we do? I can replace the -225 with the linear combination. Use our properties of matrix arithmetic to rewrite it. And now I've got matrix times eigenvector in both spots. Instead of doing those products as matrix products, I can replace them with the appropriate scalar products. So -2, 7 was associated with the -4, and 1, 1 was associated with the 5. So I could replace that matrix with the scalar, and now that makes it much easier to do this particular matrix or this particular product. You just get 44 and -64. All right, so anyway, this gives you a little bit of insight of why we care about eigenvalues and eigenvectors. And so in class, we'll do more examples of this, do a little bit more concepts, and do a little bit with how we can do higher and higher powers of matrices. That's actually section 7.2 about how you can do higher powers of matrices easily in certain situations. So like I said, we'll do more of these kinds of examples in class.